Looks like we're live.
Yeah.
Great. Hello, everyone.
Hey, everybody.
5 more minutes, right?
Yeah, 5 more minutes. And thank you to everybody that's joining us for the second day. We will start in 5 minutes. Numbers are jumping up nicely. We have 58 people in here now, 62.
That's great. Welcome, everyone. Thanks for tuning in. I hope you enjoyed day one. I definitely did.
Yeah, it was a great time. So you taking a holiday after this, Teamer?
I'm not sure if I'm going to take time off. I'm going to take time off over Christmas. But yeah, and so in 2 weeks, I'm flying to St. Petersburg, which is my home city.
Oh, nice.
I'm going to stay there for the rest of the year. So yeah, the next audio program I meet up, I'm going to be moderating from there with you.
St. Petersburg.
I'll be 3 hours ahead of you. So it's going to be very late, but it's fine.
I haven't visited Russia yet. I'd really like to visit there one time.
Well, once the pandemic is over and it will actually be kind of safe again to travel there, you should totally do this. I can give you a free city tour.
Oh, that'd be awesome.
Yeah. Well, if you're ever up for it, let me know.
Yeah.
I love showing people around.
Yeah, I'd love to visit Russia.
It's a weird place, but there's definitely a lot to see.
Yeah, I can imagine. I've been to some pretty different places. Yeah. Great. So we've got about 3 more minutes left, 2 more minutes now.
Okay.
Thanks to everybody who's joining us. We will start shortly.
I think I'll definitely take tomorrow off. I think that's a good idea.
Yeah, I will probably take Friday, Saturday, and Sunday off.
I mean, yeah, Saturday, Sunday, I'm never working on the weekend. Do you?
I work most weekends.
Oh, wow. Okay. No, I have a hard rule, like on the weekends, I'm just not touching my computer to stay sane.
Yeah, I probably need to start doing that.
Yeah.
I wanted to get a PS5, but they're sold out, unfortunately.
Sorry, what?
I wanted to get a PlayStation 5, but
I want to get one of them.
Yeah.
They're sold out?
Yeah, they're sold out.
Oh, no.
Yeah.
Yeah, I have a PS4.
Yeah, I have a PS4 as well. I've been playing Spider-Man. It's really good.
Cool, man. Yeah, I need to check out PS5 whenever it's going to be possible to buy it, I guess.
Yeah, it just came out today, actually.
All right.
Yeah, so nearly there. Should turn 1610 any second now.
All right, let me take a last sip from my
for a coffee?
Cup of tea? No, I don't drink coffee anymore. I quit drinking coffee. It's amazing, by the way.
Yeah.
So I quit drinking coffee. Now I just wake up in the morning. I'm early in the morning. I'm awake. I have so much more energy. It's brilliant.
Wow, I don't think I could ever quit coffee.
Oh, you should try, man. Like, it's so good for you.
Yeah.
All right. I actually need less sleep now as well. That's weird. Anyway.
Yeah, nearly there. Okay, it's just turned 1610. So great. Thank you to everybody who is joining us for ADC Day 2. And just a reminder for everybody who's joining us from the conference that you can actually ask questions using the Q&A panel down in your bottom right-hand corner. For our first talk on day 2, we have a very special guest. This is Timur Dumler, and Timur is a C++ developer specializing in audio and music technology, an active member of the ISO C++ community, and conference chair of ADC. He's passionate about building communities, clean code, good tools, and the evolution of C++, and he will be speaking about using LOX in real-time audio processing safely.
All right. Hello, everyone. And welcome to my talk. Can you actually see me? The Zoom thing didn't go green. I'm not sure if it works now.
Yes, you're all good.
All right, cool. Cool. So yeah, welcome to my talk, using LOX in real-time audio processing. This is a topic that actually has I've been thinking about ever since I joined the music tech industry, which was back in 2012. And it's a topic that just keeps coming up again and again and again in discussion. When I was kind of learning about like all this like audio processing, real-time stuff, and I was asking all these questions like, can I do this? Can I do that? And this topic keeps coming up in discussions. And when I was really trying to figure out, how to do this, I kept asking experts and I kept getting conflicting answers. And so that seems to be a topic that, different people have different opinions on, or sometimes is not fully understood. And so I then realized that the only way to really figure this out is to, for myself to just sit down and just, figure it out once and for all. Well, not once and for all, but like to try to understand what's actually going on by digging a bit deeper, and then also to give a talk about it so that other people don't have to go through this pain again. So this particular topic, I have actually first published a blog post about this on my website back in April. And then I also gave a kind of rough first early version of this talk a couple of months ago at the Audio Programmer Meetup that Josh and I are co-hosting together. And so now I just have like a little bit more data, a little bit more, I understand this a little bit more. So I just wanted to give this talk again in a more complete way and with a little bit more material. So what are we actually talking about? So if you do audio software, then we have this audio thread, which is doing our audio processing. And then we have this process callback, which is getting called on this kind of real-time processing thread about every 1 to 10 milliseconds, depending on the settings of your buffer size and sample rate and things like that. And then you have other threads interacting with this real-time audio processing thread. So typically you have a UI thread, and then you have a knob, and then you have things like the user turns the knob, and then you have to basically pump the new value of that parameter into the audio thread. Or you have to do the other way around, where the audio thread, you have from the host incoming automation data, which might or might not be on the audio thread, and then you have to update the knob, and display that on the UI. So it kind of goes both ways. And then you might also have, for example, a MIDI thread, where if the user is playing a keyboard, you have incoming MIDI messages, you have to pump those into the audio thread. You might have another thread that reads maybe an audio file from disk, and then you need to stream that into the audio thread as well. And so you have all these different threads. And if you look at those arrows that are red there, then those are those where basically you have to interact with this real-time audio thread. So you really have to be very careful there, because you're not allowed to block it, right? Because you have this like regular callback, which you're not allowed to miss. Otherwise, you generate a glitch. So how do we synchronize those threads with each other? And there's a number of techniques, and I've given quite a few talks in the past about various techniques of syncing those threads, in a real-time safe manner. And obviously, one thing that you can do, which is great for single parameters, is you can use atomics. So you can, set and get them from different threads, and that's going to be real-time safe. Or if you have a stream of data coming in, like what we saw with the MIDI messages, or maybe audio data coming in, you can use log3 queues. So you can push from one thread and pop from another thread. And that, again, if you've done it correctly, is going to be real-time safe. And then we have this other synchronization mechanism, which is used in programming, which I guess is the most common one for non-real-time use cases, which is LOX. And it turns out that this is the mechanism that is most popular with everyone else, but in audio, you cannot do that, because if you lock a mutex, then that's a system call. So that in itself is typically not real-time safe. And then once you're, if you can't acquire the lock, then basically you're waiting for another thread that has that lock. So you're basically blocking the audio thread for an unknown amount of time, which you can't do because you only have a limited amount of time. And not only that, but if you do that, you typically are waiting for a thread which has lower priority than the audio thread. So you have this, this problem of priority inversion. And so all of this together leads to the fact that then your probability of missing a callback and generating an audio glitch is higher than 0. And that is not good, because that basically renders your product useless, right? So if you are glitching, then that's not great. So we cannot use locks, mutexes to synchronize the audio thread with anything else. But what happens if we kind of have this problem where we need to, we have shared data between the audio thread and a different thread, which is not just a number. So it doesn't fit into an atomic. And it's also not a stream that you can push into a queue, but it's maybe a data structure, maybe a vector of numbers, like some filter coefficients, for example, right? Or something else, right? So you have a whole data structure, which is maybe a bit bigger. And then the audio thread needs to have access to that. And then another thread needs to also have access to that. And so how do you avoid race conditions there, where one thread is reading and the other one is writing in a real-time safe way? And that's essentially the problem here. And I think the proper solution to this problem is actually to not do this at all, but to use immutable data structures. And Juan P. Bolivar has a bunch of talks about this, which I really recommend you check out. The idea basically is that instead of sharing a vector of floats between different threads and basically reading and writing from different threads and synchronizing that, instead of modifying a data structure, you basically just peel off a copy which has that modification. And so then basically, instead of modifying a data structure, you create a copy of a data structure. And then you basically inform the other thread of the new data structure with, under the hood, it's just going to be an atomic pointer swap, right? So that's OK. So basically, while the audio thread, for example, is seeing an old version of the vector or whatever it is, you already have generated a new one on the other thread, and then you just swap them. And then next time around, the audio thread is going to see the new version, right? So that is kind of the proper way of doing this, in my opinion. And there's other strategies as well. So there was this other brilliant talk from last year's ADC from Fabian Renjals and Dave Rowland about Real-Time 101, where they discuss other strategies as well. But unfortunately, sometimes, especially when you're working with older code or just existing code, you kind of are stuck in this situation where you just have this vector or whatever it is, data structure, which is shared between the audio thread and another thread. And you just kind of have to deal with that. So you can't afford to rewrite your whole audio engine to use immutable data structures. You just have to deal with that problem somehow, that you have to synchronize access to this data structure. And so really this talk is, I'm going to talk about this very problem. How do we solve that problem? Like that, you kind of have to synchronize access to a data structure. And so what I did was I actually looked at typical use cases where this occurs. So when I was first putting together this material, I was working on a code base where I was working on a sampling engine. And then that had locks in various places. So I just looked at where those locks are. And it turns out these are kind of like a few typical use cases where these locks occur. So for example, an audio thread is searching a list of samples, like audio files, basically. And then another thread at the same time adds more samples to that list, like load samples, right? So that's an example where you have this like shared data structure. Then another example would be that the audio thread is maybe trying to play a new note, a new sample, and searching for a new voice to play this on. And then at the same time, another thread allocates more of these voices. So again, you have a dynamic data structure, and you have a kind of a race condition there that you can resolve with the lock. And then the kind of extreme case is that this data structure is the whole audio graph, right? So the audio thread is processing the whole audio graph that you have. And then at the same time, another thread is rebuilding that graph and maybe inserting new nodes into it. And then again, you have these race conditions that you have to resolve. And so how do we do that, right? So you see that these use cases are all kind of similar, and the only difference between them is kind of how large the amount of data is that you have to share that is kind of contended between the audio thread and another thread. But it feels like there are kind of three varieties of kind of the same problem. So how do we then actually synchronize access to a data structure like that? So we already know that we can't just basically surround it with a lock and then just lock that lock in the audio thread and in the other thread, right? Because we cannot lock a mutex on the audio thread. So what can we do instead? Well, this is something that I've actually seen people do in production code in various places, is instead of doing lock on the audio thread, they do this try-lock, right? And so it seems that this is okay, or is it? So let's try to figure out whether this is actually real-time safe. So what is try-lock going to do? So the way it's written here, it's this RII wrapper, right? So scope lock and unique lock are the RII wrappers around mutexes that we have in the C++ language. You can also, of course, call this manually, but this is just a nicer way of doing this. And so if you create a unique lock with try to lock, then it's going to call just mutex try lock. So that's what it's going to do. Is this real-time safe? Well, let's check the C++ standard. So the C++ standard for mutex try lock says that basically it attempts to obtain the mutex without blocking, and if ownership is not obtained, that is, if another thread has that mutex, there is no effect and try lock immediately returns. So basically, it tries to lock the mutex. If that doesn't work, it immediately returns. And that is in itself, so far, real-time safe. Or is it? Because mutex try lock is not the only thing that is going to be called here. We have also this brace, right? And because this is an RII wrapper, this brace is going to call the destructor of unique lock, and that's going to call mutex unlock. And what does that do? So mutex unlock potentially, if no one else is waiting for this lock, it's not going to do much. But if there is another thread waiting for this lock, it's actually going to wake up that other thread, right? And so that is a system call. And so that is not real-time safe. So you cannot do this, right? So that might try to wake up another thread from the audio thread. That's not safe. And when I actually published this first on my blog earlier this year, there were a few answers, and there was an interesting discussion. There was this person replying to my blog post. First of all, they didn't like my Spinlock implementation very much. They were talking about TAS and TTIS, test and swap, and test and swap, and this is something we're going to discuss later. But then also they were saying, well, that mutex unlock uses a futex on Linux, and so that is real-time safe. But then actually Fabian replied saying, well, actually, that's not really true, because a futex basically could cause a context switch to another thread, and it's not specified whether or not that thread is going to be woken up immediately basically from the audio thread in this case. And actually, there was also a paper basically saying that futex implementations are not real-time safe. So, it's funny because there are apparently different experts on Linux arguing about whether this is real-time safe or not. I would say that the evidence points to probably it not being real-time safe, and there is maybe some discussion about that. But when in doubt, the default should be that it's not. And definitely when we talk about Windows and then we talk about macOS, where it's not open source, you cannot even look at what's going on, then it's just a system call, right? So we have absolutely no guarantee that mutex unlock will not do anything that is not real-time safe. So for all of those reasons, well, we can't use try-lock on the audio thread. So what are we going to then do instead, right? So, basically, I should also say, so if you're in this world where we use try-lock, basically it's different from lock in the sense that that can fail, right? So if you're on the audio thread and you try to lock something, so that can fail. So you have to have a fallback strategy for that, right? So typically, if you're doing audio and you need access to the data structure and the test and the acquiring the mutex fails, you would fall back to some other strategy, right? So you would, if it's a parameter that you need a new value, then you would maybe be using the old value, or if it's like a new file that you would like to play, then you're going to play it, the next time around the audio callback comes around. Or, if it's something else, you might want to, maybe play silence or fade out or do something else. So it's probably not what you would, the ideal behavior, but it's always going to be better than an audio glitch, right? So this is kind of what we're trying to achieve here, right? So we want to have a mechanism where basically we do get access to the shared resource from the audio thread. And if we don't, we can fall back to another strategy, which is also going to be in a real-time safe manner, right? So, but it turns out that, well, we can't use try-lock for that check and that fallback. So what can we then do instead? How can we fix this? And so what, again, people in practice and in production code do is they then say, okay, well, let's use a spin lock instead. So a spin lock looks something like this. This is a very simple implementation of a spin lock. And actually, for example, so I just wrote this, but Juice has, for example, a very similar implementation, except I don't quite like the Juice one because the Juice one, first of all, it doesn't use the optimal memory order flags that I'm using here. And also it doesn't use the lock, try lock, unlock kind of STL compliant interface. So the Juice one wouldn't work with the RI wrappers that the standard library provides, whereas this does. So this you can just plug into scope lock and unique lock, and it will just work. So let's see what this does, right? So now instead of a mutex, we have this spin lock, and so we have this atomic flag, which basically tells us whether the lock is owned or not. And then in the lock, we're just going to try to acquire it and just do that in a loop. So that's why it's called spin lock, right? So it's going to like, can I have the lock? Can I have the lock? Can I have the lock? And eventually it will succeed whenever the other thread is going to let go of it. And then we have the try lock, which is just going to do this check once, right? So it's just going to check the flag once. And if that fails, well, it's going to return false. So now you failed to acquire the lock. So now you would have to fall back to your fallback mechanism. So you would call the lock from like the UI thread, and you would call try lock on the audio thread. And then we have the unlock, which just clears that flag. And if you just use that spin mutex, you see that all the operations here are real-time safe, right? Because they're only operating on this atomic flag. So there is no system calls, no mutexes, nothing like that. So that actually, if you plug it in like this into this unique lock, that works. This is a real-time safe, low latency implementation of a spin lock, which will do the job. So this is actually safe to use. Is it a good idea, though? So it will not cause glitches if you use the try lock and not the lock on the audio thread. So that's safe. But is it really a good idea to use this? So let's look again at this lock method and what it does. So it is essentially just trying to acquire this lock by just repeatedly accessing this atomic flag and querying its value, right? So it's going to just keep pounding this atomic again and again and again and again in a loop until it succeeds. And I actually tested this on my machine. It's about 200 million times a second that it tries to access this atomic. And so that's basically going to completely max out your CPU, right? So that's going to just, whatever core for example, the UI thread is on, it's going to just completely max it out until it can get the lock, right? And so that is kind of now a problem, right? Because imagine, for example, that the audio thread is also operating at a high load. Maybe you're doing something really intense, like you have some kind of really nice sounding convolution reverb going on, which consumes like 90% CPU. So now you have the audio thread at 90% CPU load doing the processing. And now you have the other thread, which is waiting for the lock, basically being at also 90 or 100% CPU, like spinning on this lock. So you have these two cores completely maxed out. And that's going to suck your battery dry really, really quickly if you're on any kind of mobile device, for example. So that is a huge waste of energy. That is, formally correct and real-time safe, but it's just like a waste of energy, and it's just not a very efficient way of solving this problem. And so when I realized this, I started kind of looking around, and it turned out that within my sphere of basically audio developers, there wasn't really anyone or anything that could offer a solution for this. And people would just keep doing it wrong. They would just keep either doing the mutex tri-lock, which is actually not safe, or they would just use the spin mutex, which is fine, if you're doing this maybe once a while, right? So if you are only waiting on this lock, if the user loads a new file once in a blue moon, then you don't have that problem. But if you, if it's something where you're interacting with the software and you have this lock that you need all the time, then you run into this problem, right? So, for example, if it's like a knob, something that the user tweaks all the time in the UI, and that now has to interact with the audio thread in this way. So how do we solve this problem? And as I said, I couldn't really find any solutions where I was. So what I then usually do in this case is I look a little bit beyond the audio industry, right? And so it turns out that there are actually quite a few kind of other industries which are doing similar stuff, which are doing kind of low latency or near real-time stuff, and specifically, finance, high-frequency trading people, gaming people, graphics people. And I happen to, be exposed to this stuff. So, for example, just last year, about a year ago, I was in my home city of St. Petersburg at the C++ conference, where Bryce L. Stanley-Lelbach, whom I know actually also from the C++ community, was giving this talk about the C++20 synchronization library. And he works at NVIDIA. And so, he is an expert on some of those problems. And by the way, spoiler alert, this talk was about basically all the new synchronization facilities that we now have in C++20, but unfortunately, none of them are real-time safe. So it's really useful to watch that talk and get an idea of the concepts. But unfortunately, when it comes to real-time audio, the only really mechanism that we have there, which we can use, which is real-time safe, is kind of atomic and stuff based on atomic. So all these other things that we actually introduced are not really, you can't really use them for real-time stuff. So I don't think that's actually going to change. So we're going to have to rely on atomic operations, I think, for forever, basically, to do this kind of weird thing that we do as audio people, right? That we do like real-time code on a non-real-time kernel, right? But anyway, so in his talk, Bryce introduced me to this concept that I wasn't aware of before, which is actually the solution to this problem. How do we make this spin lock more efficient, which is called exponential backoff. And so the idea here is that you have successive stages of like different types of waiting. And Bryce actually then showed us this implementation here of a spin lock, which is taken from the Linux kernel. And so this looks really scary. This is now Linux kernel code. But let's take this apart a little bit. So you see that the tri-lock and unlock bits are actually exactly the same as the naive spin lock that I was showing before. So we can just basically look at the lock function for now. So that's the lock function here. And so you see that the strategy here is this kind of exponential backoff in these stages. So stage one is you just do the naive spin as we did before, and you do it 4 times. And if that fails 4 times, then okay, we have to wait for this lock a little bit longer. So then let's do something else. So then we have this next thing that we have this ASM volatile, scary looking thing, which is inserting a rep not instruction, which is basically just telling the CPU to sleep, right? So this is like a low energy way of putting the CPU to sleep for a little bit. And then we do that 12 times. And if we still didn't get the lock, then we actually yield from the thread. So we just tell the thread scheduler, hey, I'm still waiting for this. So let me just, let other threads do something. And then if that fails as well, like however many times that is, 64, then we actually actively putting this thread to sleep. So there's good and bad things about this implementation. So the good thing is this rep-nop instruction is actually pretty cool, because not only does it put the CPU to sleep, but also if you are on a CPU which supports hyper-threading, which are pretty much all modern Intel chips, then another thread can actually make progress in this time on the same CPU. So that's really great. This particular way it's written with the for loop outside and the ifs inside, it's not particularly great for the optimizer, specifically not particularly great for the branch predictor, because it's going to have a mispredict every time you drop down to the next stage. And then also, it's not really portable, right? So this inline assembly thing with the ASM volatile, inline assembly actually no longer works on 64-bit Microsoft Visual Studio. Thank you, Microsoft. And then the rest is actually wouldn't work on macOS either, because it's Linux specific. So then basically what we need is some kind of platform, not platform specific, but portable version of this, right? So what we can do is we can see if there are some standard C++ facilities that could provide similar functionality. And what Bryce actually suggests in his talk is this implementation here, which uses these new features from the C++ 20 synchronization library, where stdatomic actually now has these wait and notify one and notify all functions, where basically you can say, okay, well, I'm going to wait on this flag, and then another thread can basically flag that the stdatomic value has changed to wake up the first thread. And so that is something that then is in the standard library as of C++ 20, and then basically the vendors can then decide to implement this, for example, on Linux in the way we just saw. But the problem for us audio people is that we don't really know what the implementation is going to be. And at least one standard library vendor that I've spoken to says they will probably use a Futex to implement this. So it's like the same thing as we saw in the very beginning, which we know is not real-time safe. So the problem with this is, like with everything in the C++ 20 synchronization library, we cannot rely on this being real-time safe. We cannot rely on this not doing any syscalls. We don't know what the implementation is going to be. So unfortunately, we cannot use this. All right, so we need to do something else. Let's go back to this Linux implementation that Bryce was showing. And so it turns out, so this strategy here is actually kind of tuned for a little bit of a different scenario, right? So this particular type of lock, that's from the Linux kernel, right? So it's great for scenarios where you have high contention, right? So it means that you have many cores and many threads, so dozens or maybe even hundreds of threads, which are all contending for the same lock. And if you're in this scenario, then this kind of implementation, at least on Linux here, is not just very efficient, but it's also fair, right? Because if you have been waiting for longer, then you would be so it would kind of implicitly manage like queue of threads that are all waiting on this lock. But it turns out that in audio, we don't actually really have this scenario, because everywhere I've seen in audio code where people would put locks, we typically only have 2 threads. We don't have 100 threads, we have 2. One is the audio thread, which is the real-time thread, and another one is just one non-real-time thread, like for example, the UI thread. So we have this problem with this implementation that we do actually want to optimize for a different scenario. And also, obviously, you want this to be cross-platform, right? So, I mean, we can stay with, so this is also Intel specific and this is Linux specific. So let's stay with Intel for now. But, at the very least, you want to work this on Linux, Mac, and Windows, right? Because most audio production software will be for Mac and Windows. So we really need to make this portable. So let's start. So it turns out that this ASM volatile thing that wouldn't compile on Windows, well, there is actually a way to write it like that, where if you include this Intel intrinsics header, then you have this pause intrinsic, which is essentially doing exactly the same thing, inserting exactly the same instruction. But fortunately, that one works on all of Windows, Mac, and Linux. So that's great. So the sched yield we can actually replace with still this thread yield, which is a C++ standard, again, portable way of writing pretty much exactly the same thing. And then the sleeping bit, let's just ignore that for now. So we're gonna talk about sleeping later. But for now, let's focus on these three stages that we have, which are spin, pause, and yield. And please notice that in this implementation, we have these weird magic numbers like 4, 16, 64. Where do they come from? We don't know, right? So they have been tuned for a certain use case. And then for audio, as I said, we have a different scenario for we probably need different magic numbers here, right? So we need to tune this for this use case that we actually have in this type of like audio music making software. So how do we tune these numbers? The only way to actually do this is to measure, right? So what I did first was I actually tried to figure out how long do these operations take, just measure how long a spin, a pause, and a yield actually takes. And so in order to do this, so I'm using Catch2 for my unit tests, and turns out Catch2 also has benchmarking facilities, which is great. So then I wrote this basically test harness to measure these things. And so actually I have to say, I'm not going to show this now because it's quite a mouthful. Unit tests for asynchronous code is fun to write. It's highly non-trivial. So that would be like a whole talk in itself. So I'm not going to cover that here. Just assume that I have a way of measuring how long these things take if you have this kind of lock on one thread that is spinning on a lock on one thread and then releasing it on another thread. And so turns out on those two machines that I had at the time, it looks something like this. So notice that these are just two machines that I had in my house at the time, and they both are using exactly the same CPU, this like relatively high-end i9, Intel Core i9 CPU. And one of them was a Dell Windows laptop, and the other one was a MacBook. Please also note that the y-axis is a log axis. And so we see actually exactly this kind of exponential back off idea here, right? That every stage is about an order of magnitude, takes about an order of magnitude longer than the previous stage, right? So turns out that the spin on these machines takes, like one spin takes about 5 nanoseconds. Then the pause instruction takes about 40 nanoseconds. And then the yield, that's where we see a little bit of scatter because I tested this on two machines, but also on 3 different platforms, right? So like Windows and Linux on the Dell, and then macOS on the MacBook. And it turns out that that's where we get a little bit of variation, but that's actually expected, right? Because spin and pause are basically on the CPU instruction level where we see exactly the same thing because it's the same architecture and the same CPU. And then on the yield, turns that Linux, macOS, and Windows, obviously their thread schedulers are implemented in different ways. And so we see a little bit of scatter here, but that yield takes something between 300 and 500 nanoseconds on those machines. And then, so I did that, and then I got some feedback from someone who was looking at this saying, well, actually this pause instruction varies wildly between different chipsets, right? So if you have, the claim was if you have different chips, then that pause would be completely different. So I actually then got a few kind of low-end machines. So I also had then access to a Mac Mini from 2014, which is like a much older Intel Core i5 CPU, and then also a low-end PC, which was actually using an Intel Celeron. And it turns out that yes, on those machines, the numbers are different somewhat, particularly the pause instruction, for example, takes a different amount of time noticeably on the older Mac Mini. And I also did not test this on Intel Atom or Intel Core 2 Duo, which is a predecessor architecture from the Core i5, i7, i9 kind of stuff. But I think this still looks okay. So we still see, it's not quite, there is a little bit of scatter, but I think overall we can still say that if we have spin, pause, and yield as the 3 backoff stages, that roughly we have something like 5 nanoseconds for the first, something between 10 and 60, 70 nanoseconds for the second, and then something between 200 and 500 for the third. So we have roughly still the scenario of each stage being 1 order of magnitude slower or taking 1 order of magnitude more time than the previous one. And so let's look at this yield again, because this is a bit weird, right? So what I expected to see with a thread yield is that if you yield from a thread, then basically you lose a time slice, right? So then another thread jumps in and does its stuff, and a time slice is typically something between 10 and 100 milliseconds. And so that's what I would have expected, but instead I'm seeing this like 500 nanoseconds. So what's going on there? So then I did another test where I did this test in a much more realistic scenario where like what you would have if you would actually produce music, right? So you would, I put this whole thing in a plugin, then I loaded this into a DAW, and then I have like 20 other plugins going on in that DAW with multiple tracks and other stuff going on so that the overall CPU load is quite high, and I just let that run. And then I saw that, yes, sometimes that yield would miss a time slice, and then it would take 10 or even 30 milliseconds for one yield to basically come back around in this loop. But that would only happen, more or less once a second or so. But then most of the time it would still just take those like 500 nanoseconds, this yield. And what's actually going on there? It turns out that, well, if you are yielding, like a lot of the time, there's actually nothing else that you could yield to. So most of the time, that will just, yielding in a loop will just be a busy loop, right? So if you do this yield, what the operating system will then actually do is will switch you from user code into kernel mode. It will do a context switch. Then the kernel will say, okay, you want to yield, great. So I'm going to suspend the thread, put it into the back of the run queue, and then realize that there's no other thread in the run queue. So it will just immediately resume the thread again. And those are and just keep running. And those are the 500 milliseconds that we're seeing. And basically, this is just burning cycles, right? This is just this busy waiting again, which is just burning useless cycles. So that is not great. So let's not yield in a loop. That's just not a good strategy. Let's yield once in a while. So a callback, an audio callback, takes about like 1 millisecond or so to complete. So we might basically yield every 1 millisecond or so to just, we're going to talk about this a little bit later, but yeah, don't yield in a loop because that's just a busy loop. And also the corollary from that is also don't sleep, right? Because a sleep is just a yield plus a wait, right? So and the sleep actually has another problem, because if you have the audio callback, which is getting called every 1 millisecond or so, and you're like at 90% CPU, then you only have a 100 microsecond window where the other thread could jump in. And if you're sleeping for 1 millisecond, then you're going to miss that window again and again and again. And then your GUI, you're not going to cause a glitch because you're on the other thread, but your GUI will get laggy, and you don't want that, right? So let's not yield in a loop, and let's not sleep. So that's why we're skipping this like last stage. And so now let's tune how much time you want to spend in those stages. So if you look at these use cases again, then I just kind of went ahead then into the real code again, into those places where we were using locks, and just kind of measuring how long these things typically take. And it turns out that, well, if you're just searching a vector with a handful of numbers, maybe, or a handful of pointers or something, then just checking that the vector is empty, that takes something like 25 nanoseconds on my machine. If it has just a few elements, it might be more like 1 millisecond. And then at the other extreme, we have this thing where the audio thread is processing the whole audio graph, and it's basically one kind of pass through the whole thing, and that would typically be something on an order of 1 millisecond. And so these are kind of the two extremes. So then what then I did was I have these 3 stages where I have a stage 1 where I just do this quick loop. And then basically I'm going to stay in that loop for about 25 nanoseconds, which is this time where the audio thread might be just doing something very quick, like checking that a vector is empty, and then it keeps going, and then it can release the lock immediately. So then I can just basically do this like very quick, immediate kind of spin lock thing. If that didn't succeed, then okay, the audio thread is doing something a little bit longer. So then we drop down into the second stage, where now we have this pause instruction. And so here I'm staying for about 400 nanoseconds, which is how long it might take for the audio thread to complete something a little bit more complicated. But then actually, it turns out that there is one problem here still, because then this stage 2 still is not, I mean, it's great, better than stage 1, where we spend like 100% CPU, but it still spends about 10% of the CPU time doing stuff, right? So we have this pause instruction, which is going to put the CPU to a brief pause where other threads can make progress. So that's great. But then we still have this loop around it, and we still have this check, right? So so that's not great. So we still have this like loop counter and everything. So then for the third stage, which is where we're going to do basically spend most of the time, what I then did is I actually wrote out 10 of these pause instructions. And it's kind of annoying. You can't write them in a loop because some compilers actually don't unroll that loop, and then you have like another counter again. So I had to like write them out. But now that's great, because now instead of spending like 10% of the CPU time doing work in this third stage, we are just spending 1% of the time doing stuff. And we're spending 99% of the time just not burning any energy at all in these pause instructions. And that's exactly where we want to be. That's where we want to be most of the time. And then just at the end of that, so that doing that 3,000 times is going to be this 1 millisecond. And then if we still haven't acquired the lock after 1 millisecond, then we can start to get worried, right? Because then it's like, well, so the audio thread really should have completed its work by then. So maybe something weird is going on. Maybe there's a lot of threads doing stuff and we're like on very high load, or something, the thread scheduler is doing something weird. So really we should just kind of yield once there, like every millisecond, to give the thread scheduler the chance to sort things out. And then we just go back into this like 1 millisecond loop where we're just in this very, very low energy stage. And then basically, then these numbers basically just are keeping this lock in this loop, these loops for this amount of time, right? And so I don't really like magic numbers, so you can factor it out like this into this array where you have these numbers in the front. And I also then added a comment explaining, this is where the numbers come from, et cetera, et cetera. And that's basically what we then decided to use on x86. It's not perfect, right? It's based on measurements on like a particular kind of machine. But I think it's good enough. It's a good implementation. It works. It does what it's supposed to do. And so, of course, we can, possibly improve this further. So specifically, you could actually measure on startup how long this pause instruction takes. If you're like on some kind of CPU, which is very different from the ones that I used, and then adjust the number of iterations for that. And then also depending on how long the actual audio callback is, you could actually, you have this prepare to play callback or something similar, depending on what framework you use, which is going to tell you the current buffer set and sample rates. So from that, you can work out how long an audio callback takes. And then you can basically adjust this last stage for the duration of that as well. That is quite, not trivial to like thread through this API. And so I decided to not do that, because I don't think this level optimization is very significant, because we're already doing a very good job at like spinning in this like low energy state. Then there was this question of test and swap, or test and swap, which I also don't think is very significant. So what this was actually about is someone said that, well, if you have this kind of spin lock, so this is again the very kind of simple one. Well, actually, this is not great, because if you do this test and set, that's going to write to the atomic, and that's going to always invalidate a cache line, right? So that might be very bad for performance if then other threads are accessing that atomic on that cache line. So if it invalidates that cache, so then it makes the memory access much slower on the other threads. So then one way to get around this is to basically do test and set. Unfortunately, atomic flag doesn't support just test, right? It only has test and set. So then you have to use atomic bool instead. And then you have to actually check that it's lock free. And then you can do this test and swap. And then you can also actually, if you want to do a really nice job, you can align it on a cache line size to basically make sure that you don't have this false sharing thing. So this is how you can optimize this like primitive spin lock if you use it like that. But again, I don't think this is too relevant for this use case, because you need to do all this. We have this like busy waiting flag, which is really for generic use. So if you have a lot of them, you have a lot of contention on those locks. But first of all, we do have this exponential backup. And also, we're only doing the test and swap just a couple times. And more importantly, we only have 2 threads, and only one of them is going to call lock, because we are never going to call lock on the audio thread. So I don't really think we have to worry too much about this test and swap stuff that you see here for this particular use case. But just for completeness sake, I want to show this as well. But there's one more thing that we actually now do have to worry about. So of course, Intel is not the only architecture out there. And even if you are not doing mobile applications and you're just doing desktop software, well, Apple is just transitioning their hardware to ARM chips. And we got this development transition kit a few months ago, and I'm sure many of you have had to deal with this as well, where basically now we have to port all our software to ARM if you want to run on macOS. So then obviously that thing then didn't compile. So I had to port it to ARM. And actually, it's kind of fine, because the only platform-specific bit is this pause instruction that we saw earlier. So we kind of need to find an equivalent on ARM. And it turns out it doesn't quite exist. So then basically, I remember that at last year at ADC, Ryan Brown gave this talk, which was actually dealing with kind of low-level ARM stuff, which is actually very useful. So he was actually trying to solve a completely different problem. He was doing audio on an iPhone, and the iPhone has this like CPU throttling thing where it reduces the CPU speed, which can cause audio glitches. So you need to basically keep the CPU artificially busy to circumvent that. And the way he did that was with this like wait for event or WFE instruction. And so what this does, it enters a low power state until a wake up event occurs. So low power state, that sounds good. And actually in XNU, which is essentially the Unix kernel for the Apple platforms, it just basically produces a wake up event regularly. So then it says the instruction averages 1.32 microseconds. So I thought that looks really interesting. So I then went into the ARM developer manual. It turns out there was actually a group of instructions there. There is SEV, SEVL, WFE, and WFI. And so basically, if you have, and so SEV sends the signal event across different cores, then you have SEVL, which is like a single core version of that. And then WFE waits for events or interrupts, and WFI just waits for interrupts. So basically, the one instruction which is really interesting here is this WFE instruction, which you can also use like this. So you have, you can include this ARM ACL header, where ACLE stands for ARM C language extensions, and then you get this instruction. And when you just use it like that, then what I observe is that it returns after about these 1.3 microseconds, which is actually very regular, very reliable, and is the same across all Apple platforms. So I'm seeing the same on an iPhone and also on this new ARM Mac. But then if you call ACV first, you send this like signal, and then call the WFE instruction, then it just takes 30 nanoseconds, which basically is this thing that, well, if you send a signal, then this like event, basically this event register is set, and then WFE wakes up immediately. So it turns out that this ACV instruction is actually kind of a signaling mechanism across threads and across cores, right? So that's really cool. And if you look at the how like spin locks are implemented, for example, in the Linux kernel for ARM, you actually see this here, where you have the lock actually, waits on this WFE, and then the unlock actually sends this SEV, sends the signal, which then wakes up the other thread with this like super low level instruction mechanism. And turns out that this gets really extremely deep. So depending on what ARM chip you're on and lots of other things and what kernel you're on, there's like many subtleties there in order to get this right. So I actually spent like a day just reading this ARM developer manual stuff and super low level kernel code. And then I just realized, okay, I'm not an operating system kernel developer. I'm not qualified to do this. I don't really understand all the subtleties in this code. And also, this is complete over-engineering for the problem that we are solving, right? So the only thing that we're trying to do is we want to implement this last fallback stage of our audio spin lock, which just should wait without spending too much energy. So it just turns out that we can just use this instruction, basically, which if you don't do anything else, if there's no events being sent, and I know I'm running out of time, I just need like 1 or 2 more minutes, please. Basically, yeah, we can just loop on this, and if there's nothing else going on, so that at least on Apple platforms, we'll just wait for these 1.3 microseconds and then return. So we had these 3 stages on Intel. It turns out that the second stage, which has this like shorter wait, we can't really implement on ARM because we don't have this like short pause instruction there. We have this like longer wait. But what we can do is we can just skip the middle stage and just have these 2 stages. One, which is just the spin lock, just do a spin lock a couple times, and then we just drop into this loop where we just do this WFE, which is this low energy wait effectively, if you don't get these signals from anywhere. And then I just tune the numbers here to basically, again, stay for about 20 nanoseconds in the first stage, and they stay for about 1 millisecond, millisecond, which is about 1 kind of audio callback, roughly order of magnitude in this stage. And so this is, again, not the way you would implement a spin lock on ARM that has to deal with a lot of contention, where like many threads are competing for this lock. So you wouldn't put this into the Linux kernel, but you have this scenario. If you have this scenario of a real-time audio thread and one other non-real-time thread, then this is good enough. So you can obviously tweak this further. You can, again, factor out the magic numbers. You can factor out the different stages. You can combine the Intel ARM code with if-def, so it's the same class. You can do all of these refactorings. But I leave that as an exercise for the reader. I hope you get the idea of what's going on here. Future work. So I haven't tried this on Android. In Android, I think the WFE instruction will behave differently because it's a different kernel. And also, I actually haven't published this code yet. At the moment, this is just code that I'm working with. I need to kind of extricate that from that and kind of put that on GitHub. So apologies, I haven't got around to do that yet. I'll do that soon. Because obviously you shouldn't really be implementing this yourself, right? It's like with other these low-level things, like, for example, LockVQs and stuff like that. You should not really have to write this yourself. You should use a library implementation because it's so many things that can go wrong. But it's still useful to have an idea of what's going on under the hood. So I hope I've given you that idea. And basically the main takeaway anyway is this one. Please don't use try-lock on the audio thread because it's not real-time safe. And yeah, that's pretty much it. Sorry for overrunning by a couple of minutes. I just want to say many thanks to those people who have really helped me figuring this out and patiently answered all my questions. Gaspar Asman, Dave Rowland, Fabian Vanjals, and Ryan Brown. Thank you so much for telling me things I didn't know before and helping me figure this out. And that is how you use locks in real-time audio processing safely. Thank you very much.
Yes, thank you very much, Timur. And there are so many questions that people have been asking and other thoughts on your talk. And what I've done is I've screenshotted those, and we will give Timur an opportunity to answer those in the Track A discussion that will be in the Discord channel. So the Track A discussion in the Discord forum where Timur will be able to have an opportunity to answer those questions. Thank you to everybody who has tuned in both here in the conference and also live on YouTube. And we will see you for the next talk.
Thank you very much, Doc, and thanks everyone.